talk is by Nicholas Calvert.
Adam thinks that looks like me, that's why it's up there. So good morning, everyone. I'm Nick Calvert from the University of Ottawa. I'm excited to talk to you today about a radical new contrast agent for MRI we call glucocorticosteroid. So in terms of imaging-based evaluation of kidney right now, kidney disease is a growing global issue with a 13% mean global prevalence. Right now in the clinic, the way we look at kidney function is through glomerular filtration rate, or GFR. It's the gold standard. And the problem with GFR right now is it gives us a value of what's happening with the kidney, but there is a 30% variability in this value based on its being in population-derived data. And oftentimes we don't see real major changes in GFR until kidney dysfunction is very low. And important to me as an imaging scientist, GFR doesn't provide any spatial resolution at all. There are methods to look at kidneys through imaging that give you both spatial and quantitative information, like through dynamic contrast enhanced magnetic resonance imaging MRI. But the gadolinium agents used to look at with DC MRI are contraindicated in a number of kidney dysfunctions with the real and perceived risks in some of these cases. These include things like acute kidney injury, late-stage chronic kidney disease, dialysis patients, and patients undergoing kidney transplant, where either they cannot or physicians will not prescribe DC MRI due to those gadolinium fears. There are alternative methods for kidney imaging to look at function, both qualitatively and quantitatively, but they don't really provide a one-stop shop, and they don't really provide the things that we get with MRI through DCE. There's things like CT, but a lot of the CT agents we use now can't be used in severe kidney disease patients. There's ultrasound, but the spatial resolution is low. And there's also spec-based agents, especially with technetium-99, DTPA, but again, lower spatial resolution and a metal-based contrast agents with similar contraindications. So because of those issues, the field of organic radical contrast agents, or ORCAs, has been growing, and there's been a lot of research on this. So this works similarly to how gadolinium works, where you get enhancement of the water proton, especially in T1, by those free electrons within gadolinium, but it uses the free electron that's available on a radical. Now, a lot of these in the literature are almost entirely nitroxy radical based, so that NO bond with the radical on the oxygen, especially molecules like TEMPO. But the problem with these is they have a short radical lifespan under in vivo conditions. They get quenched by redox, in vivo redox very readily. So we wanted to take a bit of a different approach on how to look at a new ORCA, and we looked at the verdazole scaffold. So this was first reported in 1959, and almost all the literature looks at this as a magnetic susceptibility agent for different physics evaluations that I honestly don't understand. But it's never really been evaluated as an organic radical contrast agent. So that's what we wanted to look at with this. So verdazole's been synthesized a number of ways in the literature, and we wanted to go back and kind of pick out the best parts of this synthesis and kind of be able to make it in a more in vivo friendly way and be able to scale it as well. So I'll quickly go through this, but we started with a Bach hydrazine with an isopropyl group. With phosgene and triethylamine overnight, we were able to produce that ureal Bach hydrazine scaffold. And then with deprotection and just incubation with D-glucose overnight through the aldehyde tautomer, we're able to close off that ring, and you get this linear chain of glucose at the bottom, which we thought would be more biocompatible and water-soluble. And then through a mild oxidation with potassium ferrocyanide, we're able to produce this in a 74% yield. And what's interesting to this, if you're not a chemist, is that we're able to do all this without running any columns at all. So we can scale up the synthesis really, really easily. So with our contrast agent made, we wanted to make sure that it actually did enhance T1 contrast like we thought it would. So if you look over here on the left, this is a T1 MRI of glucocorticosteroid in water, and we get about a threefold enhancement in that T1 contrast. And similar to what we see with gadolinium, I think in low concentrations and lower field, we don't get much change in T2. But what was really interesting to us, being that this isn't an nitroxy-based radical, is that our relaxation rate in the T1 is identical to what we saw in TEMPO as well at 0.3 millimole per second, or inverse millimole second. So the other thing we wanted to look at was the stability of this, because we talked about TEMPO-A-based agents, nitroxy-based agents being unstable in those biological conditions, so we wanted to make sure that this could improve here. So this graph on the left, for those of you who aren't familiar, is an EPR graph, and this looks at the magnetic relocation of that radical paramagnetic proton throughout the molecule. So basically, if you see peaks, there's radical activity. If you don't see peaks, there's none. So we used EPR in a number of different biological conditions to track the stability. So we looked first at mouse serum and compared to TEMPO all the way through, and with mouse serum, we don't really see any change in that radical activity. Now, the score rate, however, which is a strong reducer, By 30 minutes, you see almost all loss of that tempo radical activity. With glucocorticosteroid, we see none over 90 minutes and even longer. We wanted to look at more harsh conditions, so we looked at a stronger oxidizer and a stronger reducer, hydrogen peroxide and reduced glutathione. And again, over 90 minutes, we don't see any change in that radical activity for glucocorticosteroid. So we knew that it was really stable in both storage, which I didn't talk about, and biological conditions. We actually did have a solution of this stored in the fridge for over 365 days and saw only 70% loss of that radical activity. And we don't see any cytotoxicity with this molecule in very high concentrations, up to 25 millimolar in a bunch of different cell lines. So now we had a stable radical contrast agent. We wanted to see where it goes when we inject it into mice. So what was interesting to us is that when we did an intravenous injection through the tail vein and watched, so if you look over here, we circled some areas that we commonly see contrast uptake. So in the kidneys, in the muscle, in the liver, and in the bladder. So at 0 minutes, this is our baseline mouse. Now after 2.5 minutes, which is the first MRI scan time point for us, you see almost all that contrast is going into the kidneys, and we don't really see it in many other places. And then by 40 minutes, it's all moved out of the kidneys and back into the bladder. So it's kind of limited to the urinary system entirely. And this is really interesting because if you actually look at the glucocorticosteroid molecule, we call it glucocorticosteroid being glucose-based, but with that anomeric carbon drawn into the ring, you don't actually get any cell uptake because most of the GLUT1, GLUT3 cell uptake is driven by that anomeric position being available of the hydroxyl. And since we've removed it entirely, we aren't going to get much, if any, cell uptake, which is what we saw in cell culture as well. So I want to take an aside and just establish how we did our DCE work because it's not always readily obvious to people. So with our DCE MRI, we did these scans every 2.5 minutes with the scan settings that we had right now. We would draw ROIs on each scan over the kidney, and we'd focus on the cortex and the medullary-renal pelvis areas. And then we would produce summary plots, or just intensity over time curves of that contrast agent clearing that ROI. We also used these and took the natural log, and we were able to produce the most linear portion of this to get the half-life, or the renal decay time constant, or the K value, whichever you like the most. So with DCE, with us being able to map these renal decay time constant values, or RDTCs, this gives us an idea of how well the contrast agent is clearing the kidney. And if we map those values on top of the MRI image, we get something like this, which gives you an idea of how well this ORCA is moving through the kidneys. And so this is how we did our DCE. So we went back to the first image here and ran those DCE curves over top to see what we were getting and looking at how the actual contrast agent was moving through. And kind of what your eyes are telling you in the images is true with the quantitative data, is that we're seeing about a 2-fold increase in contrast in the kidneys by about 2.5 minutes. And then all that is moving towards the bladder, so limited to the urinary tract as well. And for us, what was really, really cool about this is with 9 different mice, that clearance or renal decay time constant was extremely consistent and very linear. So we thought this would be a really good urography agent to look at how kidney function is changing in the presence of disease. So most people go with the UUO model to start kidney disease or other various acute kidney injuries, but we wanted something a little more sophisticated. So we went with the folic acid nephropathy model. So the way folic acid or FAN works is that when you inject this intraperitoneally, there's a ton of folic acid receptors within the kidney, so it uptakes very readily. And because it's in bicarbonate when we do the injection, and as the pH changes, this crystallizes within the interstitial space of the kidneys, and it causes this damage, a lot of damage in the tubules, and so it induces acute kidney injury by 15 days. Over time, as that damage starts to heal, we get fibrosis occurring, we start to move into a chronic kidney disease model. So you kind of get to look at both things, the acute and the chronic at once. So day 0 is our healthy baseline for these mice. Day 15 is our acute phase, and day 30 is our chronic phase of kidney disease after injection. And so these are just MRI images, 2.5 minutes at our highest contrast point after injection of glucocorticosteroid. And at least to me, as not a physician, we don't really see a lot of change in these kidneys just by contrast MRI. Now, if we map those K values on top of it, we start to see that there's a lot going on here. So again, day 0 establishes our healthy baseline. If we look towards the acute phase, we see a massive increase in K value across the entire kidney. Now, as we move forward to day 30, and that chronic phase starts to happen, we get healing of the kidneys, but we do have some fibrotic areas. But if we look at this change in that K value over time, in terms of quantitative changes, we can see that, again, the images are telling us quantitatively what we see. We see an increase in K value in the acute phase, and still slightly elevated, but starts to move towards baseline as it enters early chronic phase. And what's interesting about this is that when we look at creatinine, which is one of the markers used to look at GFR, between day 0 and day 15, we don't see any major changes in creatinine levels, but we do see a massive change in kidney function through clearance. But let's talk about qualitative, because I think this is really interesting as well. We have these maps here as well, and you'll notice that day 30 does start to move in terms of quantitative towards the baseline. But what's really interesting, if you look at where these arrows are pointing right now, you start to see kind of striated regions where there's an elevation in K value still. And these are actually fibrotic regions that matched up really well with our histology through Masson stain, where we start to see these fibrotic regions left over as we enter the chronic phase. So really what we're getting is now a spatial mapping of these sites of kidney damage and fibrosis, as well as the quantitative changes throughout. But this still isn't GFR, and one of the things we wanted to do is to see if we could mimic GFR, or faithfully track GFR using this agent through the kidney, so we could look at GFR and spatial resolution at the same time. So we took a step back and wanted to see if there were other imaging methods to look at GFR through the kidneys through blood mapping, and we found something that's actually going into clinical trials right now in humans from MediBeacon, where they have basically what you're seeing here is a mouse where they shave the side, and they're able to inject a Fitzy-Sinistron probe and tape this filament to the side of it, and it gives you a curve that looks like this as the fluorophore clear, which looks familiar to what we've seen with our stuff. So what was really interesting about MediBeacon is what they were doing was they were taking the one-phase decay of this and using math they had determined beforehand with different blood testing and blood values, they're able to plug it into their own equation and determine GFR from the one-phase decay of these curves. So we would basically be able to do the same thing and determine GFR from our curves as well. So we went back and we redid this folic acid model side by side with this transdermal as well as the MRI model. And you can see that between the two, the curves of clearance in terms of raw intensity look very similar. Now, if we go through and plug our one-phase decay values into that math to get GFR between the both, this was really interesting is that at day 0, 15, and 30, we don't really see any major differences between the two in GFR, showing that we can faithfully monitor GFR as well. You do start to see a little bit of deviation at the day 30 point as we enter the chronic phase, but I'll talk about that in a moment. The reason we believe that deviation is starting to occur is because we are looking at a 2.5 minute acquisition time on MRI right now. If we start to improve the speed at which we're acquiring these scans, we'll get more data points on that curve and be able to get better calculations of these. So if you look at the transdermal model, K value, renal decay time constant, it's much slower than what we see with our agent right now. So it's able to generate more data. So one of the things we're working on in phase 2 is actually trying to slow down that clearance rate and get more data points on that curve. So that was great in terms of kidney imaging agent. We got a really good probe that would actually faithfully show both GFR and spatial resolution. But I think there's a lot more power to these verdazole probes than we talked about today. So the verdazole scaffold is a lot smaller and more modular than the gadolinium-based agents. We can do a lot more with it. It weighs a lot less in terms of molecular weight, and it's easier to work with in terms of chemical modification. We found out in some of our work as well, we have a lot less serum albumin binding than gadolinium, and we can modify these things very easily. So we want to work on improving that T1 shortening to get better contrast, and we want to improve that mean residence time. But I think one thing we really want to look at now is being able to actually do molecular MRI with this, because these are small probes. We can get these into cells, and we can change this function. So one of the ones we're working on right now in terms of a technetium-99 blood imaging probe mimic with these sestamimi groups all around the side, we actually went back, looked at the glucoverdazole probe, and I mentioned before that not having the anomeric position precluded cell uptake. We spent a lot of time and have actually generated and shown cell uptake now in these galactose-based probes. We're able to preserve the anomeric carbon at the bottom and have that tautomerization happening so we can get GLUT1, GLUT3 uptake. So just to conclude on this, glucoverdazole has generated excellent and specific contrast in the kidneys. We saw with the folic acid nephropathy model with structural and functional changes throughout, and we believe it's a potential GFR and spatial imaging agent. We have long scan times right now that can only generate a certain number of data points on the curve, but we believe that improving the MRI method to be faster and maybe using actually a lower field MRI with the radical may give us better contrast and more faithful mapping. We believe this is going to be a potential excellent alternative to a metal-free MRI contrast agent. I'd like to acknowledge my lab and especially my supervisor, Adam Schuhendler, who's always been helpful with this. And a special shout out to Dylan Berger and Nick Sheehan at the Ottawa Hospital for helping with a lot of the kidney modeling stuff. And thank you all for listening today.
I think we have time for a couple questions. Anybody have a question?
Excellent work. Have you tried this contrast agent for tumor imaging by any chance?
Not yet. We're working on it now with those new targeted ones. So the chemistry's been much more difficult than I showed it to be to actually get those sugars to stay anomerically active at the bottom. So we've got versions of it that are working now. We did a small pilot study with tumor cells or with cancer cells where we saw cell uptake. But in terms of tumor models, it's the next thing. But we need to work on the scaling right now on that side.
And also, for one of your kidney results, when you look at the acute versus the chronic the results, if I remember correctly, the intramedullary area in your acute the case is very high rate compared to the chronic cases.
Yeah.
Do you know what's happening?
Just the acute injury, even in the hospitals right now, when you look at acute injury, the clearance rate that they measure through GFR is just much higher. The acute's just a much more serious injury.
In the intramedullary
Yeah.
area compared to the...
Yeah, that is what we saw. And we actually saw that we did another model as well, I didn't show here today, with UUO, and we see that as well with UUO, where before the hydronephrosis of that, the medullary region goes, you start to see really, really high contrast uptake there versus the cortex.
Okay, thank you.
Last question of the session. It's you. You already asked one.
Oh, yeah, sure. Can you remind me really quick what the dose was for the imaging?
I think it was around, oh my goodness, I can figure it right now.
Was it high though? It's probably a lot higher than a...
It is much higher. So we actually matched it. I'm trying to remember the numbers. So we matched it to the T1 shortening difference between us and gadolinium.
So it's probably, yeah, pretty high. So I think, it's one thing, even though this doesn't have gadolinium, when you're injecting really high doses of things, you might run into other hesitancies with, renally impaired patients.
Absolutely.
But have you considered like low field imaging with these probes?
Yes, we have. We're actually working on it right now.
Yeah, because
Yeah.
I think that's, that's coming, and this is a killer thing for that,
Yeah.
as you're probably aware. Yeah, cool.
Thank you.
Additional question from the back.
I just wanted to clarify, and I'm sorry if I misunderstood. So in your animal model, what you showed was that the signal goes up when the acute phase starts in 15 days, and then the signal goes down almost to the baseline during the chronic phase, and creatinine keeps going up.
Yeah.
Is that correct?
Yeah.
So does it mean that actually this agent only good for the acute phase?
No, not necessarily. So we do start to see healing in terms of clearance, but it isn't just because the agent itself is clearing quickly doesn't always mean that the creatinine levels are going to stay the same. So one of the issues with creatinine is that it isn't directly driven by kidney clearance. There's other productive sources as well throughout the body, so you're not always going to get it through the kidneys. And that's one of the things we wanted to address, is that creatinine isn't always the best way to look at kidney function.
I understand about creatinine, but I'm asking about the agent.
Yeah.
So it means that it's not going to determine if a patient comes in a chronic phase, it's not going to see anything, right?
Maybe in early chronic phase right now, no, but it does seem to identify sites where there is issues with chronic like fibrosis. So that's what we were more interested in the chronic phase, is identifying areas in the kidneys where there's damage. So one of the things that we've talked about looking at for this right now is that one of the problems with GFR is that you're looking at the global system. If you have not even an acute kidney injury, but you have a problem in the area of one kidney, you're getting a global GFR. You're not looking at site specificity. So you think about patients with on dialysis, or even patients with transplant. If you have early kidney death starting to happen, it's going to happen in one area, but you won't immediately see a change in GFR. But you would immediately start to see a change of how things are moving there, because you'll have a change in tissue there that you'd see with that contrast agent.
Great. Well, I think that wraps up the session. So we'd just like to thank all the speakers and the audience for their attention.